In this lesson, we're going to learn one of the most powerful topics in electrostatics, Gauss's law. But before we use the law, we first need to understand something called a Gaussian surface. A Gaussian surface is simply an imaginary closed surface that we draw around charges to calculate the electric flux. Now, if you look at the picture on the left, imagine the balloon is the Gaussian surface and the light bulb is the electric charge inside it. The balloon completely surrounds the light bulb, just like a Gaussian surface completely surrounds a charge. This simple picture helps us visualize the idea much more easily. Now, the next question is, what shape should we choose? The answer depends on the symmetry of the charge distribution. For point charges in charged spheres, we use a spherical Gaussian surface. For long wires or line charges, we choose a cylindrical surface. And for infinite charge sheets or very large conducting plates, we use a pillbox, which is a short cylinder. Now let's write Gauss's law. The total electric flux through any closed surface equals the enclosed charge divided by epsilon zero. The most important idea to remember is this. Only the charge inside the Gaussian surface contributes to the net electric flux. Charges outside the surface may create electric fields, but their total contribution to the net flux is zero. Now that we understand the Gaussian surface and Gauss's law, we're ready to start solving exam-style problems. Now let's look at two more very important applications of Gauss's law. The first one is cylindrical symmetry. If you look at the picture, the Gaussian surface is a cylinder surrounding a very long charged wire. Because of the symmetry, the electric field points only in the radial direction, and its magnitude is the same everywhere on the curved surface. Applying Gauss's law gives us the final equation. The electric field is equal to lambda divided by 2 pi epsilon 0 r. Here, lambda is the linear charge density, and r is the distance from the center of the wire. Now let's move to planar symmetry. This model is used for an infinite charge sheet or a very large conducting plate. The electric field is perpendicular to the surface and has the same magnitude everywhere. One very important point is that the electric field is uniform, which means it does not change with distance from the sheet. Using Gauss's law, we obtain the electric field of a single infinite sheet. It is equal to sigma divided by 2 epsilon 0. Now look at the second figure. When we place two parallel plates with equal and opposite charges, the electric fields between the plates point in the same direction, so they add together. Outside the plates, the fields cancel each other, so the electric field is zero. Therefore, the electric field between the plates becomes sigma divided by epsilon 0. These are two of the most important Gauss's law formulas and they appear very frequently in exams. We'll compare the electric field of a charged spherical shell, a conducting sphere, and a non-conducting sphere. Step 1. Charged spherical shell. Let's start with the spherical shell. If the observation point is outside the shell behaves exactly like a point charge located at its center. So the electric field is E equals KQ divided by R squared. Now, if the point is inside the shell, the enclosed charge is 0. Therefore, E equals 0. Step 2. Conducting sphere. Now let's move to a conducting sphere. In a conductor, all excess charge moves to the outer surface. That means its electric field is exactly the same as the spherical shell. Outside the sphere, E equals KQ divided by R squared. Inside the conductor, E equals 0. Step 3. Non-conducting sphere. Finally, let's look at a non-conducting sphere. Here, the charge is distributed uniformly throughout the entire volume instead of only on the surface. Outside the sphere, nothing changes. The electric field is still E equals KQ divided by R squared. But inside the sphere, the situation is different. The electric field increases linearly with the distance from the center. Its equation is E equals KQR divided by R cubed. This means the farther you move from the center, the stronger the electric field becomes until you reach the surface. Let's summarize everything. For both the spherical shell and the conducting sphere, the electric field inside is 0. For the insulating sphere, the electric field inside increases linearly with distance from the center. Outside all three objects, the electric field behaves exactly like a point charge. Now, let's solve an important and frequently asked exam problem together. Now let's solve an important exam type problem together. If we look at the figure, we have a plastic spherical shell with a negative charge Q, and at its center there is a positive point charge Q. The radius of the shell is R equals 10 centimeters. Point P1 is located 6 centimeters from the center, so it is inside the shell. Point P2 is located 12 centimeters from the center, so it is outside the shell. Our goal is to find the magnitude and direction of the electric field at both points. Now let's solve the problem step by step. Step 1. Let's start with point P1. Since R1 is smaller than R, the point is inside the spherical shell. According to Gauss's law, only the charge enclosed by the Gaussian surface contributes to the electric field. So the enclosed charge is simply Q enclosed equals plus 5E. Now we substitute this into the electric field equation. E1 equals K times Q enclosed divided by R1 squared. After substitution, we obtain E1 is approximately 2.0 times 10 to the power of minus 6 newtons per coulomb. Because the enclosed charge is positive, the electric field points away from the center. Step 2. Now let's move to point P2. Since R2 is greater than R, this point is outside the shell. This time, the Gaussian surface encloses both the center charge and the shell charge. So we first calculate the total enclosed charge. Q enclosed equals Q plus Q. That gives us plus 5e minus 16e equals minus 11e. Now substitute this value into the electric field equation. E2 equals K times the magnitude of Q enclosed divided by R2 squared. After substitution, we obtain E2 is approximately 1.1 times 10 to the power of minus 6 newtons per coulomb. Since the total enclosed charge is negative, the electric field points toward the center. Excellent. This problem clearly shows one of the most important ideas in Gauss's law. Inside a Gaussian surface, only the enclosed charge determines the electric field.